Wiggle, 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 wiggle.
However, cryptozoology and the CFZ in particular is a very broad church, and there are people here in this room who come from each part of the cryptozoological community. There are people here who believe in a very wide and very rich spectrum of ideas and concepts. And that is why I think events like this are so important. I think events like this are terribly important because it brings everybody together. And the main thing that I've been trying to do in the last 19 years since I started the CFZ was to foster a sense of community. And now we have to look around. We have a community, we have a living, breathing community right here. Now, we're going to go on to our first speaker in a second, but I have a problem, I'm afraid. Richard Freeman's not been on stage with me this morning. It's just been a hologram, or maybe a cardboard cutout. And because we haven't got Richard Freeman to introduce you to our first speaker, we're going to have to find somebody who can. Before Richard, before Barry Tadcaster comes on stage to introduce the first speaker, I just want to say a couple of things. If you want a dinner at the pub on the Sunday night, can you please give your name to my wife, who's on the bookstall? And if you are camping here, either in a tent or in a camper van, and you haven't got a camping permit yet off Graham, he'll be back here in a minute. He's just collecting one of our speakers from Barnstaple Railway Station, and when he comes back, you could see Graham for, if you could see Graham for the parking permit, camping permit, I'd be very grateful. But I think, Richard, can you go and see if you can find Barry? I don't know where he's gone. This is the 11th Weird Weekend, and totting it all up on my fingers, this is actually the 36th day that we've ever done. This is the 12th Weird Weekend, the 36th day of lectures that we've ever done. One of these days, just for fun, I'm going to work out how many speakers and how many lectures we've actually done over the past 12 years. But I'm very proud of this conference because, to the best of my knowledge, this is the longest running, unbroken line of 14 conferences in the English-speaking world. Other conferences have been going longer, would have taken a year off here or there, but we've been going unbroken since the year 2000. But you don't really want to hear me talking about that anymore, and as Freeman seems to have disappeared, I'm going to pass you over to Barry Tadcaster and Oren Penday.
And the last time we see Freeman, he was with some art out the back. Anyway, our next guest is a Nick Wadham. Nick is a chandler from Hartlepool, and his catchphrase is, "I am sorry, Father Mahoney, I have mislaid the Argos catalogue." His talk today is entitled Pills for Miss Betsy. Thank you, thank you.
Hello there. Nice. I'm Nick from Bugfest, and my talk is about monster movies, the myths and legends of the bugs and the creatures that are featured in the last 80 years, from black and white through to modern day cinema. First of all, I would like to take you all on a trip back in time. This thing will work.
Goodbye, friend of Hagrid. Can we panic now?
Yes. So, now for the truth. Giant insects, monsters of movie, legend and myth. Before I go any further, I'd like to tell you a little bit about what we're going to be looking at today. First of all, we're going to look at some of the giants of the past. We're going to look at the Eurypterids, the giant sea scorpions, a bit of footage of the Arthropleura. Yes, I went back in time and filmed one. And we will look at the largest fossil spider ever found. It's quite a big one. And then we'll look at how they got big, where we examine the Earth's early atmosphere. And then we're going to look at limitations of size, their breathing systems, their circulatory systems, and we're going to debunk the myths. And it wouldn't be crypto if it wasn't going to look at the one and only chicken-eating spider, topic of hot debate recently, and then we're going to finish off with some information about some of the monsters of today. So, to start off with, the Eurypterids, the giant sea scorpions. They were, believe it or not, phenomenally huge, and they are, in fact, the ancestors of all of today's arachnids. Measuring up to 2 meters in length, they were part aquatic, semi-aquatic, and towards the end of their time in the sea, they were forced onto the land by predation by the giant nautiloids and the scarcity of foods during one of the cataclysm involving gamma radiation outbursts, etc., which wiped out a lot of their food. So they had to adapt, and they became semi-land, and they would scavenge and hunt in the water margins. Which is where the BBC made a huge faux pas with their Walking with Monsters episode with the giant spider, which actually, during the production process, turned out to be nothing more than a sea scorpion itself. So rather than redo everything, they just called it a Misophilae and hoped no one would notice. That would happen. Anyhow. Moving on. Not doing that again, sorry about this. It helped to practice, wouldn't it? So here you can see some pictures of modern day invertebrates. We have garden spider, the true araneomorphs. We've got the mygalomorph there in the middle. This one here, the orange bitey thing, or Pteronocardus marinus, and of course the all too familiar scorpion. And some of the early spider forms still exist today. Some species of Misophilae, they do still survive, but they're not anywhere near as big as they were purported to be. Arthropleura is another one of the giant bugs of the past, which has given rise to a number of myriapods that we have today, namely the centipedes and the millipedes. And here we've got a clip from Walking with Monsters, and Nigel Marvin is trying to give it a bear hug, but not doing very well. The thing about Arthropleura is that nobody actually knows what it really ate, because there's no fossilised remains of the mouth parts. It grew to around about 2 meters long, not 30 foot, as Primeval would have you believe, with their interpretation of Arthropleura with its huge sickle-shaped forcipules that you would find on a centipede. But recent paleontological finds have discovered that there are pollen grains contained in some of the guts of Arthropleura fossils, which would suggest, if not vegetarian, it would be at least omnivorous. Today's equivalent would probably be the giant African millipede, the Archaeospirus gigas, which we have today out on the Bugfest table. Our largest one is 10¼ inches long, but the world record for the Archaeospirus is 15¼ inches, held by a strange-looking chap who lives in Texas. Not that I've been to Texas. I don't know what people Texas. But, and I don't want to be accused of being anti-American either. So, the largest spider. Anyone fancy a guess? This fossil here, you see, is 165 million years old. Anyone fancy having a guess at how big the leg span of this prehistoric monster arachnid was?
80 centimetres.
80 centimetres? Any other takers?
79. About.
2 foot?
Yeah.
6 inches. The largest prehistoric spider known so far, and we're talking true spider, not Eurypterid dressed up or confused as a true arachnid. The largest ever spider is that, Nephila jurassica. It's stunning, isn't it? You would expect, because of where it was from and how old it is and what the atmospheres were like, that it would be huge, but it's not. It is no larger than the current existing Nephila of today. So, how did they get so big? A number of factors involving how big prehistoric invertebrates could be. The atmosphere was hyperoxic, which means there's lots of oxygen. It's very humid, which increases the effectiveness of diffusion of oxygen, which was higher in the atmosphere, 35%, and the surface temperatures were higher. All of which together improve the effectiveness and the efficiency of an invertebrate's respiratory system, which is very simple. It's based on tubes going through the body. Relies on air coming through, hitting a small puddle of liquid at the end, in the trachees, which can be increased or decreased according to how much oxygen the invertebrate needs. And then the oxygen diffuses across this moist barrier into the tissues where it is required for respiration to occur. I'm not talking respiration to breathe, respiration the creation of energy. Here we have some illustrations. Here we've got an SEM, scanning electron micrograph of invertebrate trachees. These are the fine ends here, where the majority of the gaseous diffusion takes place across a membrane, which is bidirectional, because oxygen comes in, but carbon dioxide also goes out. Unlike vertebrates, invertebrates don't have a lung system, they haven't got the bellows to breathe in oxygen and breathe out carbon dioxide, so they have to rely on the passage of gas. Larger invertebrates can actually contract their bodies with muscular action in order to aid the process of breathing, but they don't actively breathe the way we do. And here is the structure, a transverse section through the middle of a cricket type thing, and you can see how they spread through the body. And inside here we have a sealed system of fluid, or hemolymph, where all of the organs hang and are bathed in, and the trachea and the trachees all flow through to bring oxygen into the system. And depending on the type of invertebrate you are, the more complex or the more simple it will be. The air comes in through a series of spiracles on the sides of the body. So here you can see some more spiracles here along the abdomen, and there's some here around the thoracic area. And they all enter this longitudinal trachea here, and then they spread out into the trachees throughout the rest of the body and supply it with the oxygen, which there comes in, and then out comes the carbon dioxide, usually across a diffusion gradient, which helps to pump it in and out. We're going to keep it simple. Now, something else that affects them is their circulatory systems. Some invertebrates actually have a closed circulatory system, similar to us. A lot more simple, but nonetheless similar. Most invertebrates, though, don't. They have what's called an open circulatory system, which isn't very effective, but it works for them. because they're cold-blooded. They don't have the high metabolism. Now this is the bit we want to look at here in this spider. This is the heart section which pumps the blood through the capillaries and the veins, takes it to where it's needed here in the nervous system, which is this, and incidentally, here's an aside. When you see the tarantula hawk wasp, this is why the tarantula hawk stings the spider here. Its brain and central nervous system resides mainly here, which is why it stings it there and it instantly paralyses it. So it's got a lot of capillaries here where it needs a lot of oxygen for its brain to work. It's very simple. Can I eat it? No. Will it eat me? Yes, I'll run away. That's pretty much all that they think of. Or and can I mate with it? That's as far as it goes with bugs. But the rest of the body is bathed in the hemolymph. And here, a spider's respiratory system is very simple. It has a set of hook lungs, which separate from the outside where the air comes in through here, through the opening, and then dissolves across, or diffuses to be correct, into the liquid here, the hemolymph, which is then pumped up and around and through the heart, and then through into the body and back out again to get rid of excess carbon dioxide. It's a very simple system, but it's effective to an extent. And once more, the smaller you are, the more simple your circulatory system needs to be. For instance, in a locust, it's just a tube with a few smaller tubes. The tube pumps oxygenated hemolymph around the body. It brings in oxygenated blood through these pores and squishes it out through these tubes all around the organs, which is very simple in a locust. It's a huge big sac that eats and reproduces. Nothing much more. Some muscles to make it move, and that's about it. But the earthworm, by comparison, is drastically different. Here you can see the dorsal vessel, where the blood comes along here, in that direction. At the front here, we have 5 elongated pumping vessels, known as the aortic vessels, and they are the hearts. So they pump blood down to the bottom vessel, which goes down through there, all the way along the body, and then back up around again. But they don't have spiracles. Instead, they've got a larger surface to volume ratio, which makes gaseous diffusion through a constantly moist body an effective means of surviving. So, a myth. Chop an earthworm in half, get 2 worms? No. If you chop your earthworm in half here, it may survive. If you chop it here, it may survive. If you chop it much further than here, both ends will die. You don't get 2 worms because this is the part that keeps it alive. The front end will survive, the bottom end will wriggle, which is part of its autotomy process of survival. If it's grabbed, it will shed a bit of its tail. That's where the myth came from. So if you take any of the main components of survival and growth to a massive size of prehistoric invertebrates, if you take away the oxygen and the humidity, like that, they will die instantly, almost within seconds. If you reduce the surface temperatures suddenly, they will end up dying because they won't have the time to adapt to the sudden change. But you take that hyperoxic atmosphere, and reduce it over millions and hundreds of millions of years, then they have to adapt and survive. And in order to do that, you have to get smaller. Because if you're bigger, your surface to volume ratio decreases. And therefore, the way you are breathing is no longer efficient. Which is why, it's not very clear up here, but that is supposedly a 30-foot Silurian sea scorpion. Quite wrong. The tail is wrong. All added for dramatic effect. Don't you hate producers? The Silurian environment at the time was very hot and very dry. Yes, there were areas of ocean and sea where these guys would have lived, but they wouldn't have been 30 foot long. They would still have been around about 8 foot because of a number of other factors that limit invertebrate growth. This is a movie, Eight-Legged Freaks. Bit of a laugh, really. Giant spiders like that would not survive in today's atmosphere. And even in the Silurian times, this scorpion would not have lived, it would not have survived on land like that. It would have collapsed underneath its own weight. Completely collapsed. Arthropleura. Yes. We've looked at that one already. The primeval Arthropleura would never ever have been able to survive. Even if it was the true to life Nigel Marvin one, it would still have died within minutes of suddenly finding itself through the anomaly in our world. And to be that big is ridiculous. And to assume that it has venomous forcipules is a bit of a leap of imagination and faith, because we don't know. It was all done for dramatic effect, but it works. It's fun. The chicken-eating spider. So it wouldn't be crypto without a bit of crypto. It's actually nothing more than a species of Alphabetius. A big spider, actually, a very big spider, around about 9 inches long, across, 10 inches maybe. And unlike most subterranean burrowing tarantulas, they're communal, which goes against everything we know so far about tarantulas. And they also feed communally as well. But would it take down a chicken? No, I don't think so. Mainly because they're not big enough. A chicken is a nice big thing. Panthabetius is about that big. And it's not going to take out a chicken. Would they hunt communally? Possibly, but they don't live communally as adults in the same burrows. The adult mother here cohabits with her offspring, and they will have a number of generations of offspring still living in the same burrow. As you can see, those spiderlings there are more like juveniles. They're some good 2 inches across. They will eventually disperse and find their own place. But the spiders as adults do live in a very small area, so they have spread out, and they do occupy a large territory, and the territories between the burrows aren't that big either. But they don't come out and hunt communally as adults. And my main criticism is, yes, that's all very well good saying this ethno-aware spider comes and steals your chickens away, but when you find the spider and you find where they live, where's the chicken bones? Where's the vertebrate carcasses? There are none. So, it's a bit of a fail. Chicken-eating spider. I don't know. But, if there was one, for argument's sake, a chicken-eating spider would need to be around about that big in body, the size of a honeydew melon, with a leg span of around about 2.5 foot at the most. At the very least, you could probably get away with a 1.5 foot spider, which could probably subdue a chicken. Is something that big going to survive in the atmosphere today? Is it going to be able to live in our less oxygen-rich atmosphere? I don't think so. Because to me, it's not just a biological impossibility, it's an impossibility of physics as well. Fick's law states that the rate of diffusion is dependent on the surface area times the concentration difference of oxygen divided by the distance it has to travel. Which means the rate of diffusion depends on the surface area. And the further the oxygen has to travel, the slower the rate of diffusion is going to be in order to get oxygen into the body, into the right places, for respiration to occur, the generation of energy from breaking down foods into their smaller chemical components. But this is also affected by the trachea, because the trachea means there's even further for the oxygen to diffuse within the body. So that limits how big you're going to get. If you're a huge big spider, your book lungs are going to be further and further in and take more time for the oxygen to get in. So it's not going to work if you're that big in today's atmosphere. The smaller you are, the easier it is. A 1 micrometer bacterium has got a surface area to volume ratio of 6 million to 1. A bit like my brain. A fly, 600 to 1. And a small dog, 6 to 1. And incidentally, the surface area of the human lungs is around about 600 million alveoli, so 100 square metres, so a human being. That's a lot of surface area. So we've actually got quite a large surface area to volume ratio for our respiration, but bugs don't. And they're also limited by the physical structure. The legs suffer from this effect of scaling. The strength of the leg, like it says, is proportional to the cross-sectional area, and its load bearing is proportional to the mass of its body. And as its size increases, so will the cross-sectional area of the leg in proportion to the length squared of the body. But it's getting bigger and it's getting heavier, so the load on the legs is increasing proportionate to the length cubed. So they're going to be too weak to carry the load. Which is why that Silurian scorpion is a load of old cobblers. And why I think the giant chicken-eating spider is also not going to happen. It's not going to exist. It's just pure fantasy. Muscle strength is proportional to its cross-sectional area too. So not only have you got the structural integrity of the exoskeleton to consider, you've got the tension, the strength, and the energy required to move the muscles within that body, within that huge body, to be effective. And then it's draining the oxygen, it's draining the respiration. So it too is going to have to grow in its size and strength, and it's going to increase by length squared. But its weight will also increase by length cubed, so the muscles are adding weight and stress and tension. So when they say an ant can carry many hundreds of times its own weight, what could it carry if it was the same size as a human? This is what would happen. It ain't gonna happen because of the factor of scaling. Its metabolism will not have the capacity to withdraw oxygen from the atmosphere to support the respiration or demand of the body, and it will die like that. But if you took a human, scaled a human down to the size of an ant, now you're talking superhuman. Very small. Because that human, that size, would also be able to carry the same proportion to its size as the ant. But it would burn out pretty quick because of the human metabolism. We're exothermic, we generate heat, we would have a faster heart rate, our muscles would be working faster, our brains would be working faster, and we would burn out. We wouldn't asphyxiate, but we would burn out because we would have too much oxygen because of our respiration system and our circulatory system. It's true. So, to get more oxygen in, you need a bigger surface area inside you. Big bugs have trachea within their legs to expand the surface area for gas exchange, but this only goes so far. Only big things like giant stick insects, giant beetles, or anything that's huge. Because the problem is, if you put more trachea in your body, where's all your guts going to go? Your bits, your lungs, and your heart, and your muscles, and reproductive systems, and your silk glands, and your venom glands, or whatever it is you've got inside you. There is a limit to how big creatures can get. Which is again why the chicken-eating spider is a bit of old compass. The biggest known spider ever, in terms of mass, is the Goliath bird eater. Since the prehistoric times. That is the biggest one we know. Capable of reaching up to 11 inches, can weigh 175 grams, and the fangs can be 2.5 centimetres long. I should know, we had one here last year. And the world record holder at the British National Natural History Museum is Rosie, and her body length is 11.9 centimetres, and that's a big bit of spider. I like Goliath bird eaters, one of my favourites. But it's not the largest spider. Discovered in 2001, Tetrapoda maxima, the giant huntsman spider. Lives near cave entrances in Laos. It was discovered in 2001, and it can reach 12 inches across. Big body, 4.6 centimetres. Quite a spectacular spider. It was a big shock to the invertebrate world when that little baby was discovered. The largest beetle, Dynastis hercules, the Hercules beetle, or rhino beetle, or whatever you want to call it. And these bugs have that knack of putting the trachea into their legs, because the legs have got big muscles in them in order to function and move. The muscles work antagonistically, unlike spiders, where they also rely on hydraulics and muscles. They don't purely rely on hydraulics. They use the muscles to pull the legs and contract them, but they extend them using hydraulic pressure of hemolymph in the body, which is why when you find a dead spider, its legs are always curled up because the muscles have pulled the legs in. That's a big beetle. And the largest stick insect ever, Verbaticus charney, Chan's megastick. It's enormous, 22 inches long, including the legs, 14 inches in the body. It's bigger than the Australian Acrophila titan, which was once considered a giant stick insect, but it dwarfs it. And the reason it's never been known until recently is because of where it lives, high up in the trees. But it's not the heaviest or the biggest of the stick insects. The biggest stick insect is the jungle Heteropterus dentata, and they can be big and spectacular. And they too have developed the trachea in the legs. The giant death worm. Well, not really yet then, is it? This is the giant gypsland earthworm. Now you would think, why can that exist? Nick's just said the biggest bugs are this, but this little guy can reach 3 meters long, over 1 inch or 2 inches across. Look at the size of it, it's enormous. Also sometimes known as lily worms, because some of the species of giant worms have a pleasant, pretty floral smell to them. But look, it's still got an efficient enough surface area to volume ratio for it to be able to survive. Earthworms don't have spiracles. They rely on diffusion across a bidirectional membrane, i.e. their skin. Because if it's moist enough and thin enough, the oxygen will get through. It still has the closed vascular system. And one of my favourites. There it is. There's the strange guy from Texas. It's always synonymous, hat and moustache. There it is, 15.2 inches long. It's huge. Though I would dispute the 256 legs, because mine has got 324 and it's 10 inches long. Now this one is one of my favourites. We've got a nice giant centipede out there, but that one's only about 8 to 10 inches long. This guy, Scolopendra gigantea, is a monster, and it will put you in hospital if it bites you. They are highly venomous, they are highly aggressive, and these babies are also known to go out hunting for bats. They find a nice big dark cave, crawl up to the ceiling, and hang there like a Christmas tree decoration. I'm thinking of suggesting them to Tesco's, actually. I don't think they'll take me up on it. And it waits there, and the bats are flying around, and because it's such a flexible creature, the bat just goes, la 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 la, I'll catch them off. And then the inertia of the impact folds the centipede around, and the bat's done for. Because underneath the head are these horrendous things called forcipules, which are a modified pair of legs. And in here, that section, there's some massive venom glands. Scolopendra venom is a nasty cocktail of histamines, cytolysins, hemolysins, neurotoxins. Does you a lot of damage. And if you're a little bat, you're in a spot of bother. So, can they get big anymore? Nah. Never. Does the giant chicken spider exist? Nah. I don't think so. Then again, you never know. Thank you very much for listening. I hope you enjoyed. If you have any questions, we've got time to take some questions before we hand over. That's all, Greg.
Indeed. Very interesting talk, thank you. I would take issue with one aspect of your suggested size limits for arthropods. You've focused on things that have got a very long history of terrestriality of hundreds of millions of years. The largest known living arthropod is a coconut crab, which is a crustacean rather than an arachnid, relatively recent migrant onto land, but they have a body span of approximately 90 centimetres and a body length of 4 kilos. And these are obligate air breathers now. They drown in seawater, although they have to breed in seawater. So that surely clearly shows that the arthropod body plan and respiratory systems can scale up to about an order of magnitude larger than your largest spider.
Yeah, that's true, because I was concentrating on insects and the usual invertebrates. I hadn't considered crustaceans. Good point. Something that I will research. Thank you.
I wrote about giant centipedes in Hong Kong recently, and I read a report of one up to 60 centimetres long. I think it was a gigantic species. I'm not very good at converting centimetres into inches, but is that the kind of length, the maximum length? And also, do you know anything yourself about centipedes in Hong Kong?
I know a fair bit about centipedes, but 60 centimetres would equate to roughly 30 inches. That's a centipede like that. It's a big centipede, and surely if something like that had been recorded, it would have been in public record or the Guinness World Record books alone. I would question whether something like that could actually survive.
This isn't just some obscure newspaper report. I'll show you later if you like.
If you have it with you, I'd like to take a look at it.
Vernon.
I've been waiting so long for Greg to bring this, I've almost forgotten what I was going to ask. But this is a slightly different slant. I was looking at your exhibition out there, and I was thinking of the reaction of my wife if I brought home any of the things you're showing there, why do people have a kind of repugnance towards any kind of insect or creepy crawly, if I can use scientific language? Or is there some sort of, obviously there's some sort of genetic reason for it, but why do you think people sort of withdraw slightly when they see large arachnids and similar things crawling towards them?
That is a brilliant, brilliant question. And the answer is going to be a little bit longer. There are a number of factors, Roman, affecting why people are so terrified. Not overall, on a whole, every person, but some people are terrified of bugs and creepy crawlies and spiders because think about how long that history of that presentation spanned. 450 to 500 million years. We've only been on this planet for about 100,000. In comparison, we should still be living in the jungles like the indigenous tribes of Amazonia. But we have adapted and evolved quicker than we should. We've evolved in terms of our brain and our knowledge and our technology. We are still, though, however, subconsciously very firmly attached to our caveman instincts and cavewoman instincts, where if something was big and scary looking, it's like, oh my god, it's going to kill me! You run away from it. And it's a natural response, it's a phobic response, and it stems from that. And a lot of people feel really bad about it, they feel wrong, they think, oh, it's a stupid phobia, but it's not actually. It's a sensible phobia because it's your survival instinct still affecting the way you react to creepy crawlies. And the only way to overcome it is by reprogramming that unconscious response. We've just forgotten that we should be scared of these things because we're used to our technology in our houses. But then all of a sudden, poof, out comes the unconscious and it goes, oh, get that away from me.
Well, reprogramming ourselves sounds a little lengthy. Would Valium work instead?
Brandy.
Oh yes, I tried that. Yes.
Cannabis. A bit of weed, yeah, that should help.
Thank you very much.
Cognitive therapies, neurolinguistic programming, systematic desensitization, and sometimes flooding. They're all modern cognitive approaches to overcoming these sort of fears and phobias.
That's fine, thank you.
Thank you, Ronan. Great question.
You're talking about the caveman fear of something's likely to kill you. Are we talking with invertebrates an actual fear of venom, some memory of our existence back in Africa where there were potentially venoms? Are there seriously venomous spiders in Africa? I'm trying to think. Certainly in other parts of the world. But
There are some nasty spiders in Africa. I've got some babies for sale out there actually. One it's called the orange bitey thing in the trade. It's the Pteranodactylus marinus baboon spider, and it's a nasty bit of kit, very vicious. It'll bite in thin air if it moves fast enough. Yeah, there's some very nasty spiders out there, but they won't kill you, but they will make you very ill if they bit you. And maybe there is a bit of a DNA residual memory there, or it could just be that survival instinct. If it's unfamiliar, if it looks dangerous, it probably will be, I better stay away from it. Is it big enough to eat me? Yeah, I'm definitely staying away from it. It's that residual.
your average spider is certainly not big enough to eat you.
No, but it's big enough to hurt you if you get too close to them.
There are lethal spiders, aren't there?
Oh yeah, there's
The
lethal
funnel
spiders.
web, yeah.
Yeah.
Why is the baboon spider popular then if it's so nasty?
It's a forbidden beauty because some of them are actually spectacularly stunning. They've got the most amazing black and white markings, they've got orange and black and iridescent feet that shine like a purple emperor butterfly wing, all kinds of reasons. And it's a forbidden beauty. I'd love to pick that up, but I can't, but I have to respect it. Or people just want to show how hard they are. You know.
Okay, another questions? Chris,
Sorry,
at the back, please. I'm sorry, Silas.
Oh, sorry, one more thing. Yeah, Distera crocata, the woodlouse spider, I'm told I've heard conflicting things about it, that it is poisonous enough to give you recognisable
Yeah,
toxic bite, or that it's merely got big fangs which hurt a bit.
Let's clear up 1 or 2 myths then. Firstly, Dystera crocata is a good, massive beast of a spider for British standards. It has got humongous fangs and they can open 1 centimetre wide, but it is a woodlouse hunter. If you pick it up though, it will annoy you and it will bite you, and it does hurt. They can pierce the skin, they can draw blood. The venom isn't that toxic, but it will feel like a bee sting. It will make you go, oh, I shouldn't have picked that up.
Because there were conflicting things I read, that A, it was just the fangs hurting, or B, that it was actually moderately strong venom.
The venom's going to sting.
I speak as somebody who's suffered it, because when I was little I was bitten by one, and I said to my father, oh, that spider bit me, and it really hurts. And he said, don't be silly, there are no venomous spiders.
Yeah, it does, it hurts. It hurts. It's the fangs and the venom that hurts.
Okay.
But there is no such thing as a deadly spider in England. That's a myth. The Fulcus phalangioidipes is a grey spider with long, thin, thread-like legs. And they say, oh, if that had fangs big enough to puncture your skin, it will kill you. Yeah, right. No, it won't. It might sting a bit. It's a myth. Wouldn't kill you. Poppycock. And huntsman spiders, the harvestman, that's it. They can't hurt you either. They don't even have venom.
When you said the oxygen concentration went up after the first night, is that an actual measure for the speculation?
It's an estimate. Paleontologists have estimated it.
On the basis of what?
Guys with more letters after their name than I have in my name.
Well, I wonder if it were that high, you'd get a very large number of vegetation fires and birds off anyway.
I can only go on the research and what the PhDs say.
How many of the PhDs actually measure that?
I don't know, I think I have no idea. Unless you've got a TARDIS, the only way you can find out is just to go, right, let's just measure the carboniferous atmosphere. It's just speculation and estimates based on geological data, fossorial evidence, and so forth. That's how they work it out.
Okay, hang on. Get the microphone down, please.
But I think you can safely assume that with the amount of plants that were present on the Earth at the time, I think there was quite a bit of oxygen.
I think there's all different kinds of lines there and that point to much higher oxygen concentration. In parts of the Paleozoic, particularly Carboniferous, which of course is when you've got coal being deposited. I know some of the evidence comes from stomata in leaves, the little holes that plants use to expand, and the holes are much bigger than you would expect. And also evidence from oxygen isotopes. And there is evidence for continual raging wildfires, forest fires all the time in the Carboniferous.
That's brilliant, thank you. Could have said that better.
Just to point out, well, just sort of follow on from Richard's comments about giant centipedes. There are a lot of giant centipedes, 40 centimetres plus, actually reported from the Galapagos Islands, where Scarabendra gigantea is found. But there's been absolutely no evidence of anything any bigger than about 12 inches at all. Despite, I mean, the Galapagos is a fairly well-researched area, and sightings do keep popping up every so often, but there's absolutely no evidence to say that they do get any bigger than the 12 inches we've recorded. So
12 inches is the largest I've seen.
yeah, and that, I mean, it's plenty big enough for me, but
I want a 60 centimetre one now.
Here's the proof.
I want a 30-inch centipede.
Cara, I'm shocked. Are we going to let Mrs. Wadham ask Mr. Wadham a question?
Oh, don't ask her. Don't let her ask me questions.
I
I
just
don't
wanted to
understand the
say, I know about centipedes in Hong Kong. One particular, Cyril, joined a late boy club and is now performing as Cynthia. That's what I wanted to say.
Dear Lord. I've just noticed something really strange. Lily, this is your first weird weekend, isn't it? You and John Hare are both sitting at exactly the same angle, and the two of you look so so peculiarly alike.
Another question?
Yes.
Would it be possible that the lungs of the pods would work more efficiently? Not specifically because there's a higher oxygen concentration, though that might be the case, but just simply that there was more atmosphere. Because quite a lot of the Earth's atmosphere seems to have precipitated into things like chalk and limestone.
Yeah, it's that richer atmosphere that allowed the invertebrates to get so big. The rich Earth atmosphere did. That's it. It's what made them so large. Because their small surface areas for diffusion of oxygen were effective. And don't forget, they're cold-blooded, so they haven't got a fast metabolism to support. So they don't need to get that oxygen in as quickly as we do. If we didn't have lungs, we wouldn't be this big. We couldn't be this big.
Any other questions?
If bugs had lungs like we did, you really wouldn't want to bump into a mantis. There wouldn't be much left of you. Can you imagine that? Bugs with lungs? Oh my god. Right, unless there's any more questions. Yeah.
What is the biggest mantis?
Hang on, Silas.
What is the largest species of mantis then?
Oh, I know this one. My mate Mark's got one in Bristol Zoo. Mega mantis, what's it called? I can't remember the Latin name. It's a whopper.
Cameroon one.
The Cameroon one, it's huge. It has somewhere in the region of about 500 babies out of one egg case. It's huge, it's nearly enough 6 inches long. It's a whopper, I can't remember it. Say again? That's the one.
That's easy
However,
to say.
there are rumours of an even bigger one in Peru.
Sponsor me on a hunt and I'll bring you one back.
Graham Smith's already tried. Tried to get sponsorship from me, I mean, not trying to get cancer.
I'm better looking. Don't tell him I said that.
Yes, but we only sponsor hippies. Anybody else?
I can grow my hair again.
Any other questions? Well, I don't know what it is about the Wadham traffic. I've known them for years. And I just suggested to Cara once, hey, why don't you come up for the Weird Weekend? And he said, yeah, I might do. Sounded really unenthusiastic. I don't even know if Nick was there the first time because she brought along her daughter, who, apart from the fact she discovered cheesy chips, said, oh, I like writing. Can I write a review of the Weird Weekend? I said, yeah, if you like. Then she started writing regularly for the blog. Then Nick got involved. Then Lily. And Lily, do you see that bloke there? John? Oi, wake up hair. Can you wave? He's got exactly the same haircut as you. It is really frightening.
It's my son.
He's your weird elder brother separated at birth. Very, very strange. He was on actually the same quiz team as your mother last year. But you've got exactly the same haircut, so yours looks nice. Basically, the Wadham family have been inveigling themselves in more and more, until now we can't do a Weird Weekend without them. And I've wanted to have you coming up and talk for about 3 years now, Nick, and it just hasn't happened. It's just a great joy to have you along here today. Ladies and gentlemen, Mr.